Our story begins on a blue planet called Earth, in the United States.
Hello everyone, welcome to Let's Learn Together program. My name is Eva, thank you for joining us today. These webinars were initiated by Microsoft with the intention to bring exceptional educational materials closer to teachers and educators across Europe. We have started the webinar with a short video to introduce today's topic. It is my great pleasure to welcome Professor Željko Ivezić from the University of Washington in Seattle and also University of Zagreb. Mr. Ivezić is one of Croatia's most respectable scientists who's been living in the United States for the past 20 years. We were lucky enough to catch him while he's spending some time here in Croatia, and today we have a unique opportunity to hear more about his exceptional work in the field of astronomy. You will also have a chance to ask Mr. Ivezić questions after his presentation. But before that, Mr. Darko Jureković, Partners in Learning Manager for Microsoft Croatia, is here with us to welcome all the participants. Darko?
Thank you, Eva. Good afternoon, everyone, and thank you for being here with us. Let's enjoy this presentation. The topic is fascinating, and on behalf of my colleagues here in Microsoft and my own, I would like to express our gratitude to Professor Ivezić for being here with us today and sharing this unique opportunity to learn about the magnificent world we are living in. Thank you very much, and please begin your presentation. Thank you.
Željko, can you hear us?
I can. Can you hear me?
Yes, we can hear you. Go ahead.
Hello, everyone. Thank you very much for inviting me. It's a pleasure to be here. Thanks, everyone, for showing up for this session. I would like to tell you a few words today about SDSS, and let me figure out how to skip to the next page. There we go. Okay, here we go. So I would like to tell you how to use SDSS as your own telescope, how to do astronomy from your armchair, whether you're a teacher, educator, or whether just in love with astronomy. I was amateur astronomer before I became professional astronomer, and very often I use these tools I'm going to tell you about today just for fun, just to browse the sky and see what's up there. So my presentation will have three parts. First, I'll tell you a little bit about history of scanning the sky and how astronomers today are approaching this problem. I'll tell you a few words about our main source of data for these tools that we will discuss, SDSS, and then in the end, I'll also tell you a little bit about a successor to SDSS, Large Synoptic Survey Telescope, of which I'm project scientist, and we are hoping to not only get data as good as SDSS, but actually much better and 100 times more data. So that will be in the last part of my talk. So within the context of astronomy, there are three ways of doing cutting-edge science. You must have heard of many giant telescopes. Today we are in the domain of 10-meter telescopes, and very soon we'll have 30-meter telescopes. There are two such telescopes in the US and one in Europe, which is even larger, 40 meters, that should come online in the next 10 or 20 years. The main reason why astronomers build these telescopes is not to increase resolution of your images, but rather to be able to see very faint objects. So our limitations to seeing faint objects come primarily from the number of photons we can detect per unit time. And the only way to increase this number is to increase collecting area. That's why people spend hundreds of millions of dollars to build telescopes like these two on this slide from Mauna Kea volcano in Hawaii. These two twin telescopes are so-called Keck telescopes, and there is example of spectrum that you can get from such telescopes. You can do that only if you have huge amount of glass, huge primary mirrors, which are 10 meters in this case. To get better resolution, you have to avoid blurring of the atmosphere. Even for $100 in some shop, you can get a telescope that has resolution as good as those two Keck telescopes that were hundreds of millions of dollars. So the reason for that is that the resolution is limited by the turbulence in the atmosphere. To avoid atmosphere, you have to put telescope in space, and this image here shows Hubble Space Telescope. You must have heard of it. It's the most famous telescope today. It's not particularly large, only about 2.4 meter diameter mirror. So on the left, this is not bigger than an average bus. But because there is no blurring of the atmosphere, images are amazing. You must have seen many of them in newspapers, in popular media. And this image shows a core of a spiral galaxy obtained with Hubble Space Telescope. If we try to do something like that from the ground, the resolution would be about 10 times worse. So if you want to have high resolution, you go to space. And recently there is, by recently I mean last 10 to 20 years, there is a fast development in sky surveying, and that came about because of the developments in digital sensor technology. So there are those new sensors called CCDs, so charge-coupled devices, that we all have in our cell phones, in our digital cameras that we make pictures of our kids with. And the same technology was used in astronomy to increase greatly the sensitivity of observations. And even more importantly, compared to photographic technology, where we have recording of the sky recorded in a piece of plastic or silver grains, here we have numbers, we have digital data. So it's much easier to feed this information to computers and process it. And that's why these new sky surveys are revolutionary for astronomy. And equally important, all this data are public. Traditionally, astronomers would get their data, their students, graduate students would work with their data, but today everything goes to public and everybody can access this data. And that's the main topic of this lecture today, how to get to those data. So with this data, we can make sky maps. By sky map, I mean a list of all detected objects in astronomical images, and the measured parameters. So pretty pictures are pretty, but you can't do science and analysis with them. You need numbers. You need to measure brightness, color, size of various objects. This slide shows few basic steps in astronomical image processing. The top left panel is so-called raw data frame that has a lot of instrumental artifacts. And then by doing carefully designed processing steps, you get to the bottom right corner, which then is a true representation of the night sky that was detected. And in addition, for every of these objects, there are numbers that tell us their positions and so on. So why do we want to make sky maps? What can you do with those maps, with those measured parameters? So first of all, you can make discoveries of new objects. With traditional method in astronomy, you choose an interesting object and you take a big telescope and you focus on that one single object. With sky mapping, you record everything that you see on the sky, and if your sensitivity is better than what people had before, then you can discover millions and millions of new objects. Once you have detailed measurements, then you can classify those objects. You can ask, for example, what kinds of galaxies we have. Are spiral and elliptical galaxies the only kinds, or can we have more types? And with big sample, you can study this. Then you can do statistical studies of populations that you discovered, because you understand your selection criteria, and then you can ask questions, for example, do quasars change with time? And to answer this question, you need to carefully understand what are your selection effects. When you have large samples, then you can ask, give me the weirdest object in this sample, and if your sample is large, you'll find more weird objects. For example, if you go to a little town, say Sisak, which is close to Zagreb, 10,000 people, you'll find some weird people. But if you come to Zagreb, which is 100 times bigger, you'll find 100 times more weird people. And if you're looking for someone very special, you may even need to go to New York City, where 10 million people live. So more objects we have in our maps, the weirder things we can find, and usually they provide the strongest constraints on various theories of how they formed, how they evolved. And over the last 10 years, there was a puzzle coming from cosmology where the standard model of the universe includes two components that we don't understand at all, dark matter and dark energy, which make up about 95% of the mass energy of the universe, and we barely know anything about them except that they do exist. And to answer these questions, we need new, more precise and larger sky maps than we have today. And I'll get to this point at the end of the talk when I talk about LSST. So the point of putting this data into a database is that you can bypass complex image processing that I showed you in previous slides. So you don't have to do this complex, expensive thing over and over. You can first go through images, you find your objects, you measure their properties, and then you put them into public domain, and then afterwards you can do simple analysis or more complex analysis, but you can engage people going from professional astronomers all the way to kids in elementary school. And even kids in elementary school can pretend to do science because hard things are already done for them, and now they can do various analysis that is appropriate for their age. So in few words, when did we start with these ideas? These ideas are not new. Hipparchus made the first map of the night sky from Greece 3,000 years ago. We can only see about 3,000 stars with naked eye without telescope. He recorded their brightness, and then this was the best catalog for next 2,500 years. Of course, nobody will ever again make a catalog that would last that long, but that was the first one. And then this process of doing visual observations without telescope culminated with Tycho Brahe, a Dutch astronomer who lived in the 16th century, who still could see only 3,000 stars, the same stars that Hipparchus could see, but he made many instruments, mostly made of wood, that allowed him to do many more precise measurements than Hipparchus could, and that resulted these measurements that Tycho did into Kepler's laws of planetary motions. Kepler was Tycho's student. He used those observations to find how planets move on the sky, and that formed the observational basis for Newton to develop his theory of gravity. And now I'm going to skip 400 years of history, and I will go immediately to modern sky mapping, which began about 50 years ago with Palomar Observatory Sky Survey, sometimes called National Geographic Sky Survey because they provided funds. They took large photographic plates, glass plates, about 50 by 50 centimeters that would cover 6 by 6 square degrees on the sky. And they made recording of the entire sky about 50 years ago. And that was the best data source for the next 50 years. Nothing happened because technology didn't change. And when technology went from photographic plates, then we went from Palomar Observatory Sky Survey to the topic of our presentation today, Sloan Digital Sky Survey, or SDSS. I will completely skip, unfortunately, many great surveys at other wavelengths. Today, by launching satellites above the atmosphere absorbs X-rays, infrared radiation. So to see that kind of radiation, we need to do it above the atmosphere. There were many satellites with great telescopes that did fantastic surveys. I can't tell you much about it today. I can show you an example of what you see at those other wavelengths. So for example, if you look at infrared light, which measures thermal emission, you can see a cute little cat in the upper right corner. So the blue there means cold, and reddish and yellowish means warm. And so we can see that little kitty cat is healthy. It's got nice cold nosy, and then it's got warm ears and warm eyes. We can do the same. We can apply the same technology to observations of the sky. And the bottom two panels compare what you can see with your eyes. So the left panel is night sky, as you would see it with your eyes. Of course, blue lines are added. You wouldn't see blue lines, but you see a constellation Orion. And then if you take infrared detector and you look exactly at the same region, and you can see that in the right panel, you see all that emission that goes completely undetected with human eyes. And that emission comes from interstellar dust, material from which new stars are born. And all these yellow patches indicate regions of dense and hot dust where baby stars are born. Unfortunately, we won't talk much about other wavelengths today. We'll go back to our SDSS. This is Apache Point Observatory in New Mexico. The SDSS telescope, the main telescope, is in the bottom left corner. It looks a little bit weird. Most telescopes have round protection from wind. This one is cheaper to make, so we made it rectangular. SDSS, so there is some problem with fonts. I hope it's not too annoying. So SDSS was the first survey, the first astronomical project that utilized that new technology, CCDs, to observe the sky. And in the lower right panel, you can see schematically SDSS camera, which used to be the largest digital camera in the world. It has 120 megapixels. And 15 years ago, it was the largest such instrument in the world. Over the last 10 years, SDSS obtained precise measurements for about 400 million celestial objects, about half are stars, half are galaxies. And then all these measured parameters were put into a public database. And this very fact of putting data in public domain and making it easy to download this data and play with them was essentially a revolution in astronomy. That was the first time that something like that was done. And since Microsoft is our sponsor today, it's appropriate to mention that Jim Gray, who unfortunately disappeared at the ocean a year ago, a little bit over a year, he was one of the main database developers for Microsoft. He joined forces with Alex Saleh, professor from Johns Hopkins University, and together they developed this new portal. So these things are made by people, and here is a slide on the left side of the intellectual leader of SDSS, Professor Jim Dunn from Princeton University, who used to be my boss, the best boss I ever had. So SDSS was so revolutionary that Jim was awarded a National Medal of Science by President Obama, which is the highest award in science we can get in the United States. Of course, Jim couldn't have done it alone, and the bottom right corner shows a little bit over 100 people recently at a meeting in Paris who are developing SDSS, and many of them worked on the first two phases of SDSS and data we're going to see today. So next slide shows an example of sky scanning. It doesn't look very impressive at all, and that's because there are many more pixels in these images than your display can show. I I showed 12 strips because that's how that camera got the picture, got the scan. So first, third, fifth, seventh, all odd scans came from one night. If you go back to Sloan Camera, you can see that those colored rectangles, they are CCDs, those sensors that detect photons. Different colors stand for different filters, so we can make color images. And in between two vertical columns, you can see gaps, and those gaps do not contain pixels, and when you make picture of the sky, you have gaps. But then the following night, you fill those gaps, and what you get is image like on this slide, and that's how you fill the whole sky. And so if you look at the fourth one from the left, slightly below the middle, you can see a little patch of light. Doesn't look very exciting, again, because I downgraded resolution to make all those 12 fit on the screen. Two of these strips are as wide as the full moon. So this is large area on the sky. If we zoom in, then we see objects like this. So the patch, little patch of light from the previous page, it's one of these galaxies. It's, I think, the bottom right, two spiral galaxies. These are examples of objects that SDSS recorded. These are color images. And for each of these objects, there are measurements, there are numbers that go with them. All this data is available to you publicly from SDSS Sky Server, from SDSS public portal. Next slide will show a view of the galaxy in a little different direction than on this slide. So our galaxy, the Milky Way, looks very much like the one in the bottom right corner. It's a spiral galaxy, it has spiral arms, and we are not in the center of the galaxy, we are about halfway on the way out. And these galaxies are very flattened, they look like pizza pies. So the one in the bottom right corner is looked face on, and the one in the upper right corner is looked at edge on. And so when SDSS made observations, most of these fields on the sky were obtained perpendicularly to the disk. And so if you look around the galaxy in the top right corner, you can see some stars, but not very many, because SDSS wanted to focus on galaxies, on external objects, not our own galaxy. But some scans were made along the disk, and that's the next impressive slide. This is what happens if you point SDSS telescope along the disk of the Milky Way, and then, of course, you see many more stars. And our software automatically detected all these stars seen in this image, measured their properties, and that's all available for use. You can get to this data if you go to our website. You just Google SDSS and you'll get to this site. And there are many excellent tools that you can access. You can navigate around the sky. You can search for particular objects by ID, by coordinates, and so on. There are many things you can do as a professional astronomist and as well as an educator or just astronomy lover. In particular, there is linked with exercises that is designed specially for teachers. And on each of these slides, you can also see the exact web address, so you can repeat all these steps later if you want. Why are these exercises good? Those exercises that we designed for teachers. Well, they are designed to be used with students. So they have step-by-step instructions. They have solutions to all problems and exercises. They're not just a bunch of questions that a bunch of professional astronomers came up with, but they were carefully designed and solutions exist. Another attraction of this site is that you work with real astronomical data. They are not simulations. They are not something fake. It's true data. And for many of these images, there are millions of them. It is plausible that nobody else ever looked at a particular image that you would find. Indeed, there are some teachers from Holland that discovered new objects that are now named after them. So you can have your kids develop familiarity with faint night sky, the sky that they cannot see with their naked eyes. While doing that, they will meet digital technology. They will learn even without knowing they are learning. And they will get introduction to physics, astrophysics, chemistry, some hard sciences that are not hard, that are not easy to get students to love. And all the technical knowledge they absorb is not astro-specific. We are not making new astronomers. We are making just people interested in technology and in science. They will learn how to work with large databases, how to interact with them, how to visualize data, how to read, how to make and read graphs, how to do statistics, and so on. These are all very useful in any field. And indeed, astronomy is one of the most efficient methods to attract students to so-called STEM professions. STEM stands for science, technology, engineering, and mathematics. So typically when you get a student and you talk about STEM professions, they are suspicious. But if you show them astronomy images, they usually get very excited. And we can use astronomy as a vehicle to get more kids interested in these hard professions. I think that's one of the main reasons why we should fund astronomy and astronomers. So let me go back to those exercises. So what can you get from there? So first you'll need to register. This doesn't cost anything, but just for people who develop this site to write reports to their funding sources, they need to know who, when, and how, where from access this site. So they force you to register. It takes 30 seconds. It's not very painful. Once you're registered, then you can access other pages. There are specially designed pages for students and for teachers. And the projects are designed to be appropriate for different levels of background knowledge and for different ages. Again, the font is a little bit shuffled, but hopefully that's not a big deal. So on this page, you can see basic projects, advanced projects, research challenges. These are the hardest. You have stuff for kids and so on. Those projects vary from very simple ones. Here is an example of search for asteroids based on SDSS data that in principle we can do even with kids in elementary school. I played this game with my daughter and she was second grade and she loved it. So basically what happens is that while SDSS camera is making images, the sky is turning around because the Earth rotates. And then there are a few minutes between making exposures in different filters, those little colored squares I showed you earlier. And in the right panel on this page, you can see three little dashes, three little lines, blue, red, and green. And that happens because asteroids move on the sky during exposures. And so you can find a lot of them just by inspecting images for this signature of either lines or just a little colored dot as seen close to the middle of the middle panel or close to the middle of the left panel. And so this is not very hard mathematically, doesn't require any hard math knowledge, but it's excellent for kids who are youngish. And then those exercises vary in complexity all the way to advanced SQL-based searches for subsets of data. SQL stands for Structured Query Language, and it's a language that is very popular in database domain. And for example, kids, by looking for some special objects in astronomy context, will learn this language that they can then apply in any other context. Indeed, you can make your own database and do various other things. Kids could make database with all their toys or all their Legos and then search in SQL. Just kidding, a little bit. And then another great tool that I often use just for fun is navigation around the sky. You can type in coordinates. For example, in the top left corner, you can see rectascension and declination boxes. You type coordinates, and this tool automatically takes you to the point on the sky given by these coordinates. And then you have lots of options that you can use to visualize better what you're looking at. Then you can also zoom in, zoom out. This is now zoom in to the center of that galaxy from previous slide. You can explore. If you look at the bottom right corner to those radio buttons, blue ones, second one says explore. By clicking on that one, you can get more additional data about this object. If you are interested in this particular object, you can get detailed Sloan measurements. You can even get spectrum that carries a lot of information. And for example, by looking at this spectrum, astronomer would immediately realize that this is not an ordinary galaxy, that it's got those emission lines, those spikes, and that tells us that it's a galaxy that has a black hole in its center. And so kids can learn the same thing by following those exercises that are available from that site. This is not the only way to access this data. So there is SDSS site that I showed you in last few slides. There is also a great portal developed by Jonathan Fay from Microsoft called Worldwide Telescope. You can download the code or you can run a web client and you can look not only at SDSS data, but also at plenty of other surveys. It's really beautiful astronomical site. There is equivalent of WWT called Google Skies, similar to Google Earth. that was developed by Andy Connolly from my department in Seattle. I had the pleasure of having a dinner with those two gentlemen, and they agreed that both their sites are great. They can't say which one is better. Both are excellent. They have fantastic functionality. And the data quality they put in is sufficient even for scientific work. So it's not some second-hand data. This is best that there exists in the world today in astronomy context. And again, why would one do that? You can be in love with astronomy, or even if you're not in love with astronomy, again, astronomy is one of the most efficient ways to get students to be interested in STEM professions. This is an example of Worldwide Telescope Portal. So you can see there are many different objects you can choose to look at. There are many different surveys. The site is very mature. There are a lot of things you can do. And similarly, Google Sky also offers many fantastic things that one could only dream of 10 years ago. You wouldn't even dare to dream about, something like that. So these are great tools. So to conclude this first part about SDSS, in one sentence, SDSS does everything. It does science, but it also brings astronomy to every home, to every school, wherever people are interested in the night sky. I have a few minutes left, so I'd like to tell you a few words about a project that I'm very excited about. I work hard. That's the main thing that I work on, that I've been working on for the last 5 years and probably for the next 15 years. It's a successor to SDSS. So if you liked what you saw about SDSS in the last half an hour, then you'll just love what you will get from LSST in less than 10 years. So SDSS was the first digital color map of the sky. So before SDSS, we didn't have digital data for a large fraction of the sky. SDSS scanned 1/4 of the sky and got mostly 1 or 2 photographs, pictures of the sky. So it's not a movie. With LSST, we will observe every point on the sky, over half the sky, twice as large an area than SDSS. We'll observe it about 1,000 times, and that's why we call it digital color movie of the sky. This is example of this is design of LSST telescope. This telescope doesn't exist yet, but soon we will start building it. We already have some of the main components. It's going to be much larger than SDSS, 8.4 meter mirror. You can see two people standing next to it, just to give you a sense of the size. In the heart of this telescope is a large mirror and large field of view. And the large field of view is what distinguishes LSST from any other telescope. There are other 8 meter and 10 meter telescopes. One example is Gemini South Public US Telescope in Chile, which has almost the same mirror, but it has much smaller field of view. So if you look at the upper right corner, that's the field of view of Gemini, and in the bottom right corner, it's field of view for LSST. And that's the secret, so to say, for LSST. We can scan the sky much faster than any other telescope, and that's why we can observe the whole sky over 10 years, 1,000 times. You can ask why other telescopes do not have such large field of view. There are basically 2 problems. One is to make such a large field of view and maintain the image quality. And image quality is important to astronomers. And the other problem is that if you have such a large field of view, then you have to pave it with some detectors, some sensors, and that's very expensive. So the first problem, how do you get large field of view and small image distortions, is solved in LSST case by novel optical design. Telescopes typically have 2 mirrors, primary and secondary, and that's it. While in LSST case, the primary mirror is only the outer edge of this structure in the top left corner. That looks like primary mirror, but only the outer edge is primary mirror. You can follow the blue arrows and you see the path of photons. So they come from the top, bounce off the outer edge, which acts as primary mirror, go to the mirror in the middle, in the top of the picture, that's secondary mirror. And then it goes down and bounces off the middle part of the structure at the bottom, which acts as a tertiary mirror. And it has different radius of the curvature than the outer part, than the primary mirror. And this optical trick allows you to have a large field of view and to have very good image quality. And then once you have this large field of view, then you pave it with a lot of detectors, and I'll get to this in a second. We already have this mirror thanks to a generous gift from Bill Gates and Charles Simonyi, who also worked for Microsoft. They helped us, before we got federal part of the construction funding, they helped us to get early into the queue at University of Arizona for making such large mirrors. You cannot buy them in Walmart. You have to have special order, and you have to wait in line for a few years. So we have this mirror, and now it's almost polished, and it's the main component of the telescope that I showed you earlier. This is a scheme. This is designed for the camera. It will be the largest astronomical camera ever built when it's finished in a few years. It's about 3-ton camera with 3,200 megapixels. Those megapixels pave the focal plane, which is shown here. So in the top left corner, each little blue square is one sensor, one CCD, 4K by 4K. So it's got 16 megapixels. And 9 of those are together put in a so-called raft, which is shown in the second half in the right panel. They act as an independent camera. They have their own independent electronics, and essentially it's standalone device. So if something breaks with one CCD or raft electronics, you pull it out and you replace with a spare. And so this modular design with 189 16 megapixel sensors gives you this huge pixel count of 3 gigapixels. And in comparison, the top left corner shows a typical SDSS image. The size of this image is about 1/10 of the full moon size. And the same area on the sky was observed with another telescope to sensitivity that we expect from LSST over the whole sky. And you can immediately see that there are many more objects in this image, and that there are more details about individual objects, and that's exactly why we want to build LSST, to get more objects, more galaxies to study cosmology, and to get more details about individual objects. And you look at the data, SDSS collected about 20 terabytes worth of data. 10 years ago, that was a huge amount, and we liked to compare it to the volume of all data at the US Library of Congress, which supposedly holds all the books, or most of the books ever printed. Now, when we go to LSST, LSST will collect over 100 petabytes, 100,000 terabytes of data. And this is data volume equivalent to all the words ever printed in human history from Gutenberg to today, including periodicals, newspapers, books, everything. That's about 100 petabytes of data. Of course, we get scared when we think about such large volume. So we are very careful about developing our software. We'll have 20 billion objects in LSST that we have to continuously monitor. But all this data, just like the 20 terabytes from SDSS today, all those 100,000 terabytes of data will be available to you in few years like SDSS is today. So when you play with this data, when your kids are playing with SDSS today, you can think of it as you are preparing them for the next generation data set that will be available in few years. So I will stop here. Thank you very much for coming. Here are a few slides that we went through. So SDSS was designed as a science survey, but today it's a public resource, not only in US, but it's public resource for everyone in the world. And not just scientists, but to educators and all people who love to look at the night sky. So thank you very much for coming, and I would be happy to answer any questions that you may have.
Željko, thank you so much for this wonderful presentation and for sharing your work with us. It is very impressive. I have to admit that my knowledge of astronomy is not very wide, but this presentation definitely occupied my attention. Actually, I can't wait.
Glad to hear that.
I can't wait for the night to fall to have a good look at what's surrounding us. Okay, so let's see if we have any questions from the participants. If you have any unanswered questions about astronomy, this is the chance to get the right answer. Just to remind you, you can ask questions orally by turning on your microphone or by using the questions and answers tool. By the way, an interesting fact that I read about Mr. Ivezić is that he is the second most quoted Croatian scientist. That is pretty impressive. I have also found out that you have developed a strong interest in astronomy when you were just 10 years old, and that one of your teachers is actually to blame for that. So, from your experience, what advice would you give the teachers that are here today? What is the winning approach to make astronomy interesting for kids?
Well, astronomy by itself is very attractive because not only that the night sky looks beautiful, but there are some big questions associated with astronomy. Like, for example, how did we come here? What was the origin of the universe? What was before Big Bang? There are all these big questions that kids like to ask, and the best way to make them remain interested in asking such questions is to encourage them to ask them and help them find the answers. Even if you don't know the answer, you can help them find it today on internet, in library, through contacts with professional astronomers or scientists. There is lots of information, so never tell a kid, oh, this is not important question, or this is stupid, or always encourage them. Even if I don't know, usually when kids ask me questions, I know a smaller fraction of answers than when I get questions from my professional colleagues. Kids have this ability to ask innocent questions that are very deep, and often you can't get a good answer. But don't give up. Say, we'll find it together. Help them to be curious. Help them to remain interested in science, in technology, and you will be amazed and surprised how much they will accomplish.
Okay, thank you. I'm going to ask you a technical question, since most of our participants are teachers today, and I assume that a lot of them connect to the internet in their schools. So a technical question would be, when you approach SDSS data or Google Sky or Microsoft tool, what are the requirements for that?
I think broadband internet connection should be more than enough. I don't know if people are still using modems today.
In some schools, maybe, yeah.
It is possible that you would get into bottleneck if there are some high resolution graphics. I know that in SDSS, when we developed Sky Server, we were careful to downgrade all the images. So those images that I showed that you can browse through SDSS site, they are downgraded. There are JPEG images that are downgraded exactly because of the problem of bandwidth. If they downgraded Google Sky and WWT images, I'm not sure. I would think they did, but I don't know technical performance requirements for them.
Okay.
But I think broadband should be more than enough.
Okay, I'm sure that's pretty useful for all the teachers here. Do you cooperate directly with any of the schools in the United States? Let's say in certain programs, do students come to you, come to see SDSS live?
They often come. Sometimes we organize it for the whole classrooms. The whole classes come to talk to us. More often, there are kids who are interested in astronomy who go one step beyond other kids. And then we usually have one-on-one interaction with them. And I myself had so far about a dozen high school students who came to me and said, we love astronomy, we love math, we would like to do some science project. And so all those dozen kids, they worked over summer for a month or two with me. And all of them were so good, so useful that they ended up being co-authors on science papers. So all 12 of them have 1 or 2 science papers to show to their name during high school age.
Mm-hmm. Another question, how would you compare, if that would be the right word, compare the level of astronomy in the United States with astronomy in other countries, let's say Croatia, if that kind of comparison, if that word can be even applied to astronomy?
I think US is a bit more advanced in astronomy, both professional and education and public outreach. It is hard to give a robust answer. I can tell you what I think based on my experience. It's not based on any deep statistical analysis. But based on what I heard over beer from my colleagues, we often talk about answers to this question. So in the professional context, astronomy needs expensive toys. And many of the best toys that we got over the last 50 or 100 years in the US came from big private donations. I told you about nice gift from Mr. Gates and Mr. Simoni for our project. Palomar telescope was built with such a gift. Mr. Moore, who was co-founder of Intel, he just gave $300 million for development of the 30-meter telescope in California. And the list is long. In US, people who can afford it, wealthy people, have much easier time contributing their funds, their gifts for science development than in Europe. And it's just a statistical fact. Why is that so? I don't think I can easily answer. But people in US, wealthy people, are encouraged to do so, and the community appreciates that. In the education and public outreach context, again, I think US is a little bit ahead. And I think the main reason for that is that they realized that today it is harder and harder to attract kids to these hard professions that in the States they call STEM professions: science, technology, engineering, and math. Everybody wants to be today a lawyer or a businessman or something along those lines. Everybody is scared of hard sciences, of physics, of chemistry, of math, and it's not easy to recruit kids for these professions. And it was realized a decade or two ago in US that astronomy holds this special attraction to young minds. And under quotation marks, we can cheat them into STEM professions by allowing them to play with astronomy. And for that reason, there are lots of funds and lots of encouragement in US for astronomy work. For example, if you get a science grant from National Science Foundation, which you compete based on science, you can, after you already got your funds, you can say, I will have some kids to work with me. Can I get more funds to support their participation? And you get more funds, no questions asked. I think US is providing leadership in this area, and I don't know how it works in Western Europe, but I would guess that they are not as advanced in this realization that astronomy is fantastic for getting kids into hard sciences.
So the main differences aren't actually in the knowledge itself, it's more in the financial support, right?
Right, but so time is finite. So if professors will spend, say, 10 or 20% of their time working with kids, they will have, on average, that much negative impact on their grant work, on fighting for funding for their graduate students, and so on and so forth. So, as we say in Croatia, you get as much music as you pay for.
Yeah.
So it all comes out in the average. You have to support it. You cannot count on professors who are already overworked that they will just now jump up and down with happiness to spend another 3 hours per day working with kids. You have to support it, but it has to be done in organized fashion, and you have to see what you are getting for your money. And apparently the system developed in US is working quite well. And we could copy some elements of that system easily in Croatia or other countries similar to Croatia and just learn from US. They often stumble upon problems before other countries, and naturally they come with solutions earlier. And so we can save some of the pain just by copying what they already developed.
Yeah, understandable. So you're spending some time in Croatia right now. Are you spreading your knowledge to Croatian scientists and teachers?
I'm doing my best. My time is finite, but I was fortunate enough to get invitations and find time to give about 10 public lectures. I had several professional lectures at the Institute for Science in Zagreb, Ruđer Bošković, at University of Rijeka. I went also to nearby countries, to Austria, to University of Ljubljana. I'm going next week to University of Belgrade. So I think there is spread of the knowledge, but of course one person can do only that much. So I hope if one kid was interested in astronomy because they heard my lecture, then I think I accomplished my goal.
Yeah, I hope hopefully there will be more than just one. Okay, so if we don't have any other questions, I think we have come to an end of another successful webinar. Željko, it was a pleasure to have you with us here today. Thank you again for finding the time to join us.
Thank you, Eva. Thank you for inviting me.
I would also like to thank everyone for participating. I hope you'll join us again. Watch out for our next webinar. You will receive an invitation into your inbox. If you have any comments or ideas, feel free to write to us. You can see the email address on the screen. And I hope to see you again very soon. So everyone have a nice day and see you soon. Željko, thank you again.
Bye-bye.
Bye, everyone.
Thank you very much and have a nice day. Bye-bye.
Bye.